So here you see the overall architecture of INDIGO. So on top, we have the AA planner. That's basically the brain of all the efforts here. It communicates via mission RApps to the multi-operator SMO. And then the multi-operator SMO has connectivity to different simulated operators, SMOs, and their simulated networks. We're using here simulators because nobody let us play in real life so far. And that's also very convenient to develop and test and experiment what happens. The main part is here, one of the main focus are here the TMF APIs between the multi-operator SMO and the single operator SMOs, and then of course all the interfaces to all the other components. One click, please. In this demonstration, we have basically 6 steps. So the user, think about a governor or a general or something like those positions, they are creating after a disaster happens or when a mission is needed, they create basically a mission using the mission UI. That's step number 1. Then it hits the AI planner. The AI planner does all the calculations based on information which exists already. So we do not show here in this demonstration how all this information goes into the AI planner yet. We are just focusing here on service / slice provisioning. Then once the AI planner has created a plan, which basically is a list of tasks, all these tasks will be converted into TMF APIs so that it can be sent as a one task for all the operators which are available here. It goes one service request in a TMF API to the multi-operator SMO. Maybe you can click again. So I'm explaining here also the 6 steps. So we are in step number 4. So we are processing the service order on the multi-operator SMO and forward them to the different single operator SMOs. The single operator SMOs then also consuming the checking their availability and convert those data into the request for RUs and DUs mainly. So it needs to be converted into 3GPP APIs and O1 and Open Front Hall APIs from the O-RAN Alliance. And at the very end, the network is configured. So this flow is basically what we are going to demonstrate. Next slide, please. And in order to do so, we need to come up with an idea of networks. First we created a very huge network, and the development complained and says that's too much, and we do not have so much resources. So we have here a very small network for each of the different operator A, B, and C. They are covering almost the same area, but not exact the same area. So you see the combination of all the 3 areas and their coverage areas on a map on the right side. In the upper right corner, you always see an image of the architecture and highlighted where we are. So we are down in the network that is currently the coverage of a certain area before any of the disaster happens. Next slide, please. Here is how we are going to simulate those networks. You cannot read it. That's also not necessary. I hope you can read operator A, B, and C on top. And below that, you see a list, and these lists are Docker containers. So these are software functions containerized, and most of them are DUs and RUs. So we are here in the small network simulating 21 DUs and 21 RUs. And then the rest is our owner-based smoke components based from the OEM project, from the O-Run software community. So all this here is open source based. And we have it 3 times for the 3 different operators. And this way we can easily simulate disasters by stopping these Docker containers. Next slide, please. Here is how this looks like on each of the operators. You see basically the list that all the components that use and are used are connected. You cannot read it. Maybe one click, please. So in the URL, this is an image from a browser. In the URL, you see that there is operator A. So we have operator A, B, and C. All are deployed in the Cosmos lab. We have an INDIGO space in Cosmos, thanks to Ivan, that we can do all our experiments there. And on the lower right corner, you see that all the 42 components are connected into one of the single operator. The image is exactly the same for all the other operators, so that's why it is here for A, B, and C, just one slide. Next slide, please. Still before the disaster, we created one for each of the operators, one slice, which is a kind of default slice. It has a slice discriminator. That's a 3GPP term. It's like a slice identifier. It's not exactly the same, but it's similar. And this is 6 times F, and that is basically a number which is used as a default value for all the slices. So when we start, we have one slice available for all the operators, which just should simulate here that, yeah, okay, we have coverage by default and normal operations for all the subscribers, for all the operators. It just happens. We are still before the disaster. Next slide, please. And now the disaster happens, an earthquake or something. We had in the last 4 months, I think at least 2 hurricanes. Then think about the fire on not Honolulu, but it was in Hawaii. It was Hawaii. I'm sorry. And when we kicked off here, basically the development, there was just this earthquake in New Jersey. So those kind of disasters. Next slide, please. So now what happens? The coverage of our networks are not fulfilled. All these red marked or orange marked areas are not covered by the operator, but if we put all the operators together, then we still have some coverage. And this kind of information is now given to the AI planner so that the AI planner has a view of the network, and the MOSMO has all the information about the services which are still available, so that the AI planner can do its job based on the on this kind of new information. Next slide, please. It's just the same thing, just removing the failing areas. Next slide. So here you see again all these 3 operators, and highlighted are all the failing resources. So in our simulation, we stop about 20% of the resources of each of the operator in a kind of random way. And this information is known by the AI planner. So, and I think next slide is then something about the AI planner so that Kostas can talk about it. Next slide, please.
Okay, so you've heard from Martin about the AI planner. some things, and all I'm going to do here is to recap and maybe emphasize a couple of points that may not have been entirely clear. The first one is that the planner does not get into each individual operator's network. It does not try to micromanage any of those networks. The planner comes into play only when there is something that involves multiple networks. And of course, the main point of the planner, or well, one of the main points is that it's much, much faster than a human being trying to coordinate all these activities. So the planner, a central component of the planner is what we call its knowledge base, which consists of a bunch of methods that embody expert knowledge, expert networking knowledge for creating slices. So when the planner is given a task to create a slice, it takes a snapshot of the situation, which means a snapshot of the topologies of the individual networks, a snapshot of the resources that each operator has that have survived, that are operational, and what sort of service capabilities they advertise that they can perform in the condition that they're in. So the planner uses this knowledge base of methods plus network information to take the slice creation request and break it down into an appropriate sequence of steps that the individual operator SMOs must execute in order to provision the slice. Next slide, please.
Sounds good. So I'll take it from here and we can walk through the Mission UI use case a little bit more. And the main idea is that the Mission UI is how the users who are actually trying to respond to these disasters will be able to communicate the mission parameters and different boundaries associated with the slices they wish to create to the AI planner, who will then be executing for the MO-SMO. So Roger, do you mind if I take over from the screen there and kind of walk through an example use case? Beautiful. So what I'll be showing in a moment is a live version of our actual UI for the MUI. So we were in the slides. This is the actual live version on the Cosmos servers as we're talking about. And similar to the slides you saw a couple back where we're trying to represent the cell coverage of 3 different operators, we can see 3 different colored hexagons throughout this area, which are indicating those coverage of the RUs that are still in operation. Because this is a disaster scenario, we do have a few of the coverage volumes that are grayed out. These would represent towers that are down or connections that are not available due to the disaster themselves, bringing them offline. In the context of the operator, our main goal is to figure out how we can reestablish an area of functional coverage, and we'll do that momentarily. So the first thing I want to point out is on the right side, we see a variety of different parameters: resilience, bandwidth, and security. These are how we can inform the AI planner of the needs of the network slice that we have. So for example, if we're trying to deploy search and rescue drones or something similar to help recover people from this disaster, we might need a very high resilience bandwidth, we might need very high bandwidth connection, whereas resilience may not be as important. So with the parameters specified, we can then enter a drawing mode to designate what is the coverage area of the slice that we want to create. So in this case, we have a simple hexagon, or we have a simple polygon that's encompassing the area. And we then submit this to our backend system. We'll talk about what happens behind the scenes here in just a moment, but the main idea is that the mission boundary and mission parameters are coupled together, sent to the AI planner that does the searching for how to reconfigure the networks in order to fulfill this requirement, and then ultimately goes through a translation layer to the MO-SMO, which is what is going to start working with each of the individual operators themselves to make this slice available. So with that, the MUI demo is done, and I'll hand it off to our next presenter who'll talk a little bit about the MO-SMO actions underneath the hood.
Okay, so then it's Martin again. I'm going to share my screen to see what happens on all the other layer. I hope my screen is now visible. This is exactly the same UI which we just saw, so we don't need to go this. John already hit the submit button. Then it hits the MO-SMO UI, and okay, you see before there was nothing when I started this page. Now suddenly we have here a couple of information. So the one below here shows that the AI planner has created a service order or received a service order. So on that level, it is completed. And according to the plan, I think I can look. There is a plan available. So this is a plan, and it has all the nice information about the plan and TMF APIs. The plan is now decomposed. And it looks like that the operator B and the operator A is affected by the plan, which means that they need to reconfigure something out there in their network. The operator C, which is also simulated but is not part of the plan, so that's why there will be no service request to the operator C. I think I need to refresh it again in order to see if the in process has changed to completed. Let me do it my way, how to do things. So now you see that the operator B and A, they confirmed that they have received the service order and has processed the service order. Dave, is that correct so far?
Yes, that's correct. So just to highlight all the interactions, the service orders that you're talking about are TMF 641 based. So that's the standards-based interface and format that we use to receive the service orders from the mission app, from the AI planner. And then after processing with the internal logic, then the MO-SMO will operate on the affected domains. And in this case, as you're pointing out, it's operator B and operator A. And each of those are interacted with via the TMF 641 interface to request a service order into that operator's environment.
Thanks. So then we go one layer down and can check what happens on the TMF provider on the single operator SMOs. I have also a graph here. This just all is in a simple browser. These tabs are automatically refreshing. Again, each column is one of the operator A, B, and C. We see that there is a service creation. This is in GMT time frame here. So we just got the service order on operator A and B. Operator C, as shown before, is not affected here by the replanning of the AI planner. Then once these information are now spread and sent as requests, as configuration requests to the network. So for this one, we have here, this is a situation before something happens in one of the simulated DUs from operator A. If I now refresh this page, we will see that a new slice is created. It has a slice discriminator number 1, and that indicates that now in this on DU level, in this particular DU, a new slice was created. Similar things on the RU. RU has a different interface. We here see also that there is a new line here created, which means that a new public sector slices is called here. Here you see again this service identifier. You see it here is active. So we have created here for the user plane a new slice. And the same thing we can also see now on the operator B. I switched to operator B and go to one particular DU. So also here, there is a new slice created. And if we go to the related RU and refresh this page, then we see before and after the creation. So we have here now also slice created. So this shows the entire stack from the mission UI through the AI planner, through the MOSMO, through the single operator SMOs, to the network components in the RAN network that we have configured everything with TMF APIs and ORAN APIs. And that concludes here the demonstration.